Good morning, and today we're going to go a little deeper into how we interpret the results from a binary logistic regression model. And the first 30 or so lines of the code are the same as the introductory lecture on binary logistic regression. We're going to use the odds and ends package and the duplicate package. We're going to load the Titanic dataset. We are going to do some data tidying. We're going to convert survived into a 1 and a 0, which is our binary outcome. We're going to make age numeric. We're going to make class numeric as well. That's lines 14 and 16. Lines 18 through 26, we are going to convert class into a numeric variable where 4 denotes the crew, and 1, 2, and 3 are first, second, and third class. And for a slower version of explanation for all these, you can go back to the previous video. We're going to restrict our data set to just the 5 variables that we're looking at today, which are survived, age, gender, class, and joined. Joined being the location that a person boarded the Titanic. We're going to omit the missing values, which takes away, I believe, 12 records from the data set, leaving us with 2196. And these are the records that have missing age, or missing joined, or missing class. Okay, and model number 1 is a generalized linear model where survived is a function of age, gender, class, and where joined. And of course we specify the data equals Titanic and the family equals binomial of logit, which is our syntax for logistic regression, binary logistic regression. Okay, so that's model 1. We look at the odds and ends for model 1, and we see, again to review, that age is not significant in this model because the confidence intervals include 1, but gender was highly significant. The confidence intervals are centered around about 0.1, which means you were about 10 times as likely to die if you were a man versus a woman. And for class, we also see that a higher numeric class, meaning second, third, or fourth class in the case of crew, gave you a higher risk of death. And as we also saw, there were a few places where you could have boarded Queenstown and Southampton where you had a higher likelihood of death. Now, I did look a little bit more into this, and the passengers who embarked in Queenstown and Southampton were much more likely to have been crew, and much more likely to have been of those who were passengers, more likely to have been in third class. Now, you say, well, we've already adjusted for class. So what I'm saying here is that even among the crew and among the third class passengers, those who boarded in these 2 locations were still more likely to die than other members of the crew and other passengers who boarded elsewhere. Alright, and so you could imagine within the crew there is itself a class distinction between the skilled crew and the unskilled crew, if you will, and we're lumping those all together here, but we see some evidence that the crew probably deserves to be stratified further, and that's why you see a significant effect of where you boarded. Okay, model 2, I'm doing the simpler model where I'm only looking at gender. And if we look at the odds and ends result for model 2, we see that, of course, there's only one variable, and that is gender, and the risk of dying was close to what we had before, right? So here the odds ratio is 0.09. Before, the odds ratio for being male was 0.11. Not too much different. And so we're saying if the gender really absorbs the bulk of the explanation, then how is it possible that you can have significant variables of class and where joined, but they don't affect the results? And when I say they don't affect the results, I'm referring to the accuracy of the results, the sensitivity and the specificity. Okay, so in our single variable model, the sensitivity was not very good, barely over 0.5. So not much different than a coin flip. Our specificity was very high, on the other hand, 0.91. And in our 4-variable model, the sensitivity and specificity were 0.51 and 0.91, virtually the same. In fact, they are identical. So how is it possible that we can have very different models with identical results? Again, another way to look at this is look at the contingency table, the confusion matrix, right? So accurate predictions in the first model, 357, who we predicted to live, who lived. 1362, who we predicted to die, who died. And then we have in the off diagonals the errors. And in our single variable model, we have the exact same numbers, 357, 1362. So our more complicated model is telling us that we have significant variables, but they add nothing to our sensitivity, specificity, or accuracy. So how can this be? This would seem to make no sense. Well, one way to explain this is to put the results into a single table. So I'm using the cbind function for column bind, so I'm combining the original Titanic data, the fitted values from model 1, so those are the predictions, and the fitted values from model 2. And we're putting those side by side, and I'm going to name those columns model 1 and model 2 just to be clear. And so if we look at the first 6 rows of the results, okay, so now we have whether the person survived, their age, their gender, their class, where they joined, the likelihood of survival, or the probability of survival according to model 1, and the probability of survival according to model 2. Now, since model 2 only had gender, and there's only 2 genders, male and female, there's only 2 probabilities. Either you were male and you had a 20% chance of surviving, or you were female and you had a 73% chance of surviving. And when we're making predictions about individual people, we round the prediction to either 0 or 1 to make our prediction. So if you have a 20% chance of surviving, we're going to predict that you didn't survive because the probability was less than half. Right? Now you could say, well, we think that 20% of these people are going to survive, so why don't we pick 20% of them to survive and 80% of them to die? The problem if you do this is that your results are going to be less accurate than if you simply predict that everyone will die, because you don't know which people are among the 20% who will live. So you can't really just randomly choose 20% of them to survive. You have to say that they're all going to die, right? So you round off to either 0 or 1. Similarly with the women, with a 73% chance of survival, we round up and predict that they'll all survive. And that gives you the most accurate model prediction when you do that. Okay, so now we move over to model 1, where we've added all this information. We've added age and class and where they joined. And we see now we have all different probabilities, right? Instead of just 2 probabilities, we have a different probability just about for every person. Now, two people with the exact same age, same gender, same class, same place of embarkation, they would have the same probability. But on the screen right now, we don't see any examples of that. All 6 have unique combinations, and we have 6 unique probabilities. Okay, so the first 4, because those probabilities are less than 0.5, they get rounded down to 0. We predict they would not have survived. The next 2, because their probabilities are above 0.5, we round up to 1 and predict that they would have lived. And as it turns out, you end up getting the exact same results as Model 2 because the added variables age, class, and where joined only change the probabilities by a small amount. So we have 0.2 changing to 0.18, 0.17, 0.22, 0.21. Alright, so for example in rows 3 and 4 we have children. Children were a little more likely to survive, and indeed their probabilities of survival go from 0.20 to 0.21, 0.22, a little bit higher. We have in rows 1 and 2 we have an adult in row 1, his probability is below 0.2, it's 0.18. In row 2 we have an adult but also a crew member, class 4, so his probability drops down even lower to 0.17. And then in rows 5 and 6, again, because we have combinations of age, class, and where joined among females, we see rows 5 and 6 with a lower probability than Model 2, but still above 0.5, and so we round up to 1. And so that is how, in a binary logistic regression, you can have significant predictors that in the end do not actually change the prediction. Seems like a bit of a something that's a bit non-intuitive, but hopefully you'll understand it now. So, thank you for watching, and this actually will be the last original video of the semester. We will have a few homework reviews, but this will be the last video with original content. So, thank you for your attention throughout the course, and we'll talk again soon.